So yes, I'm Jeroen Famaey from IMEC in Belgium, and I'm the WorkPackage 5 lead in Hexa-X-II. And WorkPackage 5 is about future devices and flexible infrastructure. And today I will mainly talk about the first part of the work we did in WorkPackage 5, which is on characterization and classification of 6G device classes. But I'll also give already a peek preview of the technological device enablers we are working on. So here you can see overview of WorkPackage 5. So we have 4 tasks. The first one is task 5.1, classification of novel 6G device classes and infrastructure enablers, where we look at types of devices that will be there in 6G networks, but also at enablers like reflective intelligence services and other capabilities like JCAS, security capabilities, energy harvesting, and so on. Then we have 3 technical tasks where we study different technological enablers to achieve the requirements of these new types of device classes. The first one is about hardware and RF transceivers in 6G, where we focus mainly on sub-terahertz and also components. The second one is about general purpose versus specialized system-on-chip connectivity, where we look at the trustworthiness and security of SoC connectivity, and also at different types of enablers and accelerators like AI and signal processing accelerators and energy management components. And finally, in task 5.4, we focus on low power devices, looking at the trade-off between power, costs, material usage, energy consumption for low power devices, looking both at the devices and the communication design. So let's start with the classification of 6G device classes. This is work we did in the beginning of the project. And these device classes are also described in a lot of detail in Deliverable 5.2 of Hexa-X-II, which is already publicly available on the project website. Of course, first we need to know what do we consider a 6G device. So in the Hexa-X-II project, we define a device specifically as an end node that is connected to the network infrastructure through a radio interface. It can be uniquely identified and that generates or consumes application data. And these devices consist of an RF transceiver, system on chip, which has a CPU, memory, peripherals, and also the necessary firmware and software. And we use the top-down approach, where we started from the different use cases that have been identified for 6G, both in the Hexa-X-II project, but also in the previous Hexa-X project. From that, we distilled devices and characterization criteria of devices, and then we try to group them into different device classes. So I won't go into detail on the use cases. This was already discussed in much detail yesterday during one of the previous Hexa-X-II presentations. But based on those use cases, we identify devices and then we try to characterize them. We set the basis to understand if different 6G devices fall into one device class or another. We identified numerous characteristics concerning the device. So you see them here on the right, such as the energy-related characteristics, energy consumption, storage, source, the lifetime of the device, its mobility patterns, different communication aspects and requirements, such as synchronization requirements, spectrum use, data rate, latency, reliability, and so on. We also looked at computation capabilities and AI, localization and sensing requirements, including the accuracy and security aspects. So then we try to identify these or quantify these characteristics for each of the devices, and then we ended up with 6 device classes, of which 3 are actually enhancements of existing 5G device classes, and the other 3 are novel classes we identified for 6G. And we focused in the first deliverable on 4 of these. I'll start with energy neutral devices, which are very low power devices that have very low requirements in terms of reliability, latency, and data rate. And you can see them on the bottom left of the graph. Energy neutral devices make use of renewable energy, for example, by harvesting ambient energy directly or by wireless power transfer. And they can be used for different types of applications like asset tracking, industrial monitoring, inventory management, smart homes, basically any application where you don't have very stringent requirements. And then the enhancement of massive machine type communication is the next device class, and that's an evolution of energy neutral devices, because these devices have a primary source of power, like a primary battery. So they are more reliable and they can also support higher data rates. The use cases are a bit similar, but they can be used, for example, in healthcare monitoring, which is more critical than some of the other applications where energy neutral devices can be used, but also for smart cities and industrial monitoring, depending on the reliability requirements. A new device class we identified is a reliable high data rate with bounded latency, which means we combine very high data rates up to several gigabits per second with some latency and reliability requirements. And a representative use case here is extended reality, which has strict requirements in terms of latency, but they are not at the level of URLC, for example. So they are in the tens of milliseconds rather than sub 1 millisecond. But these applications require much higher data rates. Then high reliable and low latency device class, or HRLL, increases the reliability and latency requirements, but decreases the data rate requirements. We're thinking about cobots, industrial robots, use cases such as industrial automation, telesurgery, digital twin, and so on. And then the two remaining ones, the enhancement of EMBB and enhancement of URLC, we did not consider in detail yet in the first deliverables of WorkPackage 5 of Hexa-X-II. So those will be considered at a later stage. Then, of course, we are also looking into the technological enablers. So we're doing research at how to enable the requirements of these new and existing device classes for 6G, focusing mainly on the device and infrastructure side. The first aspect is how can we achieve these very high data rates in the range of gigabits or tens of gigabits per second per user. For that, we are looking into sub-terahertz transceivers. And this links back to the work that's being done in WorkPackage 4 on radio design, which my colleague Ahmed presented before. So we closely work together here with WorkPackage 4, looking more at the transceiver side, and they looking more at the radio side. So first topic we're looking into is dimensioning of the transceiver architecture, comparing and optimizing different types of architectures like hybrid or fully digital, partially or fully connected. And we've really been able to optimize there the energy consumption, so energy per bit, which has been the focus of this work. And we've achieved savings of a factor 10 or even 50. So that's immense power savings that we could achieve by optimizing these architectures. We're also studying and developing models for hardware non-idealities in the transceivers, especially sub-terahertz transceivers, which can then be used for the radio design. We look at the PA nonlinearity, phase noise, IQ imbalance, DC offsets, and so on. We're also studying the phase noise and a local oscillator, asymmetrical local oscillators, looking at wideband phase noise versus the achievable data rate, which is very relevant for the very high wide bandwidths that we have in sub-terahertz. We're looking at alternative architectures based on new technologies like resonant tunneling diodes for sub-terahertz. And these resonant tunneling diodes, they represent a promising candidate for sub-terahertz frequencies because the architecture is much simpler compared to conventional transistor-based technologies. And finally, we're also studying switch beam antenna lenses. These are lenses that collimate the electromagnetic waves and providing beamforming gains as an alternative to phased arrays for sub-terahertz communication. And they have some advantages compared to those phased antenna arrays. We're also looking at reflective intelligent surface design. This also links to one of the previous presentations. We are looking at reconfigurable RIS tiles at millimeter wave frequencies. Tiles can be combined into a RIS prototype. They are 16 by 16 unit cells. And also at the system integration, mainly from the point of view of the control interface of the hardware. There's other research ongoing where we look more at the integration into the network architecture and radio optimization. But of course, once you have a RIS hardware prototype, it needs to be controlled by the network. And we're there looking at different approaches at how the control interface should look like. Should it be controlled by the radio infrastructure or the user equipment or in another way? Another important aspect is the system on chip design. We are mainly interested here in developing trustworthy and secure connectivity between the hardware and software components. So we're looking at application isolation, isolating the untrustworthy components of your SOC to prevent them from attacking the device. And obviously, they're looking at the impact this has on the overhead, so minimizing the security overhead impact, for example, in terms of energy consumption of your SOC. An important challenge there is how to integrate the hardware accelerators that we're also looking at. So these are the digital signal processing and AI capabilities that can be integrated into the SOC at the hardware level to enable, for example, AI-based radio design. So you have an accelerator on the device to perform AI in a very efficient way, energy efficient way. And finally, we're looking at multi-source energy harvesting and power management components that can be used to predict energy consumption and energy harvesting on a low power device. So this is especially focusing on the energy neutral devices, and can also combine the power from different energy harvesting sources to improve the reliability of this type of devices. And that brings me to the energy neutral device technology. So there we have two main research areas. The first one is analyzing the trade-off in RF wireless power transfer. So there we studied, for example, if power beacons for wireless power transfer can be cost effective for massive IoT. Also taking into account that obviously when transferring power wirelessly, there are some losses and you need to get power beacons need a lot of power as well. So there we also looked at using renewables, so green energy to power the beacons that then wirelessly transfer energy to the devices. We're also looking at onboard energy harvesting, as I mentioned in the previous slide, and also at how to optimize then the device, the protocols and applications on the device in an energy aware way, so that with this very limited amount of energy that the device is harvesting, either through ambient harvesting or via wireless power transfer, how to use that optimally. So looking at intelligent duty cycling, uplink, downlink scheduling in the network, developing new types of very low power protocols for 6G that are connectionless and self-contained, because the current generation of low power protocols we have in 5G, like NB-IoT, are not efficient enough, power efficient enough for energy neutral devices. And also at exploiting tiny machine learning type of algorithms to optimize the device. We built machine learning algorithms that can adapt their execution to the energy that's available on the device, and that can then be used to optimize the application, do onboard processing, or even do network optimization on device by optimizing the parameters. We're also building some proof of concepts. So here you can see an example of one of those proof of concepts of an energy neutral device or a zero energy device that makes use of ambient backscatter. So it basically uses ambient mobile network signals and then backscatters, remodulates and backscatters those to user equipment. And this can be used, for example, as a batteryless beacon that can localize user equipment in a building or outside. And we've done several tests in a lab environment, but also in Paris on the Orange network in a real setting, a realistic setting. So that brings me to the end of my presentation. To summarize, in Hexa-X-II WorkPackage 5, we are studying future devices and flexible infrastructure. We looked at new types of device classes like energy neutral devices, high data rate devices with bounded latency, devices that require both high reliability and low latency, and enhancements of existing 5G device classes. And we are studying enablers to achieve the requirements of these new types of devices, such as hardware and RF transceivers in the sub-terahertz range, design of RIS hardware, specialized and trustworthy connectivity in system-on-chip components, and ultra-low power device design, looking at power consumption modeling, wireless power transfer, ambient backscatter, and energy-aware protocols. If you're interested to hear more, we already have a deliverable 5.2 on characteristics and classification of 6G devices published on the Hexa-X-II website. And in a few weeks, we'll also have the first version of all these technology enablers described in deliverable 5.3, which will be published early March this year. So that was my presentation. Thank you.